the statisticians seem to be compressed into the middle of this this day, which isn't a bad thing, a statistician sandwich. And I know this is meant to be a session where we're looking forward to the next 5 years, but I think my contention would be that if you're going to do that, you need to have the basics right. And that's why a lot of what I'll be talking about this afternoon is linear regression. Thanks also to Adam Butler for helping keep me on the straight and narrow with this presentation. Now, it's an odd thing, I've often thought, being a statistician, because many people have stats software on their desks, and therefore they think they can dispense completely with statisticians. I mean, I know Bill earlier was talking about the idea that you could replace a lot of field equipment with perhaps one bit of kit that could do things automatically, and then you might have the prospect of field ecologists being redundant, because anybody could then just go out into the field and just point a mobile phone at something and it'll tell you what species it is. Well, statisticians have felt like that for a long time. And this quote here from Stuart Hurlburt, which I received a few weeks ago, actually summarised a lot of my feelings on this. He said, statistics is a strange discipline, because most courses in stats are not taught by statisticians, texts tend not to be written by them, and a lot of literature of statistical criticism isn't written by them, which is an odd state of affairs in some ways. By the way, this editorial will make a reappearance later on. Oh, it does work now. Yes, as part of this, now, I mean, I work at an institute and I work with hydrologists, I work with analytical chemists, I work with soil scientists, and I have experience of submitting papers to the two journals in those disciplines, as well as ecology. And I have to say, in terms of trouble we get from referees with the stats, I think ecological journals is the area where we get the most difficulty. I mean, it's undeniable that the level of statistical expertise within the ecological community is much higher than in any of those other disciplines. That's very true. Which is kind of odd why one of my hobbies is picking up reviews of statistics that aren't just bad reviews in the sense that they reject the paper, but they're bad reviews in the sense that I think they're just totally inaccurate. For example, I've been criticised for using SAS to fit mixed models, because apparently SAS was big in the 1990s, and I should be using R these days, or the R statistical computing platform, they said. I've been criticised for fitting a 5-level factor as a fixed effect, when I should have been fitting it as a random effect. That was the first review we got. The second review, when I did fit it as a random effect and got a 0 variance component, they told me that was because I didn't know what I was doing and I didn't know how to fit random effects models. They seem to be unaware that this can actually happen and that it's not just an error of the user. And things like I've been told I should have used generalized additive models when I've had binary covariates, or telling me I should fit mixed models when I've got absolutely no factors in my data set at all, and I could not imagine what I could have fitted as a mixed model. But one thing that's more contentious is, and perhaps the most common criticism that I've had levelled at, is that I haven't used AIC's information criterion. Because there seems to be this, I've called it in the title, the cult of AIC, as in it's something you believe in rather than something for which there's evidence. So what I thought I would do is try to examine some of this evidence. So the two key questions I want to ask today. By the way, AIC, I use AIC, okay? There is a good use of AIC, there's not a problem with that. So my purpose here today is not to say don't ever use AIC. I'm really sort of focusing on this contention, the statement that we should always use AIC if we're doing model selection or model comparison. So the two questions related to this are, firstly, is this correct? And the second one, why isn't it? So I'll first start. Now, when I thought, what should I talk about today? I thought I really am fed up talking about p-values. I seem to be always talking about p-values, and it's a bit like when you've got a toothache and you can't stop prodding it even though it hurts. I keep talking about p-values, but I don't really want to. But I almost decided not to, but then there was something happened, not in ecology, but something happened, and I thought I ought to. I think the more interesting bit, I think for me at least, because it's new, is contrasting AIC with BIC, these two different information criteria. And we've done some simulations which I think we've done some simulations to try and clarify what the differences are between these two things and what the base properties that they're supposed to have may not necessarily hold. And then there's some random stuff. Okay, that's the point. Is AIC universally better at model selection or model comparison than anything else? What I'm not trying to say is that there is any one winner, because the simulations that we will hopefully see will suggest that in different scenarios, a different approach might be relevant. And which method you choose should really come down to all sorts of different things, such as context, what the purpose of your analysis is, what assumptions you're prepared to make, and even to the extent of the properties of the data that you might have. Yes, so I'm looking at ordinary regression models, which you might think is a backward step in some ways. But I'm doing this because if you use ordinary regression models or GLMs or so, then it's easy to count the number of parameters or degrees of freedom. If, on the other hand, you were to move to something like even simple mixed effects models, or some sort of smoothing like a GAM type model, it's then a little bit harder to count the number of degrees of freedom. So then calculating things like penalties in AIC become difficult. And that's a separate area of contention which I don't want to focus on just now. And if you've got correlation structures in models, well then it's even harder, because that doesn't necessarily just impact the number of parameters in your model, but it impacts the number of effective data points you've got. So, and that would apply to temporal correlation models, spatial correlation, phylogenetic correlation, anything like that. Fit. What do we mean by fit? This is an important question, and often I think this is not dealt with very well. Anybody, if you're given a scatterplot of data, could open up MGCV in R, fit a GAM with 1 billion knots, and obtain an absolutely perfect fit. But of course we don't do that. And the reason we don't do that is because that is overfitting, and in that scenario what we're actually doing is fitting the noise or the random variation in the data rather than the signal. So that's why we need to penalise fits. So when we talk about fits, we're really talking about penalised fits. You can improve any fit by simply increasing the number of parameters, but that may be, like I say, you'd run the risk of overfitting. And different approaches have either different strengths of penalty or different forms of penalty. And I'll come back, hopefully at the end, to the idea that all of this could be thought about as a form of model misspecification. Because if we're doing some sort of model selection, selecting variables that might go into a model, getting that wrong is a form of model misspecification. So 3 ways of comparing likelihoods. I mean, I'm assuming we're fitting a regression model, we fit the model, we get a likelihood, and what might we do with that? Because the likelihood by itself, of course, is an estimate of fit. But as I say, we can improve that always by simply over-parameterizing. So we need to penalize things. And the 3 different approaches that we're going to look at, AIC, Akaiki's information criterion, the Bayesian information criterion, and a likelihood ratio test. So this is the p-value world. Now, okay, I've got my maximum likelihood set of parameters, theta hat. I compute the deviance minus twice log likelihood. And then the AIC is simply that plus twice the number of parameters. With the BIC, it's a different penalty. It's a stronger penalty, you notice, for any reasonable sized data set. It's p log n. The likelihood ratio test, of course, is something different. That's directly comparing a difference in deviances and relating that to a chi-squared with a number of degrees of freedom, which is the difference in the number of parameters. And of course, there is a corrected form of AIC which adds a second order term, and that increases the penalty for small sample sizes. But for large sample sizes, it should be roughly equivalent to the AIC. If we're comparing models, we'll be able to compute a difference in AIC. So that's what this delta AIC is. So we have a difference in AIC. And if we compare that with the likelihood ratio test statistic, we see that it only differs by this quantity here, which is twice the difference in the number of parameters. And it's worth saying, I think, that if you're trying to compare 2 models that have the same number of parameters, then the delta AIC is exactly the same as the likelihood ratio test statistic. And one criticism that's often leveled against the likelihood ratio, or doing sort of p-values here, is that your models which you're comparing have to be nested, and you can't compare models that have different sets of variables but the same number of parameters. Well, the point in that case is that you don't really need to, because if you're comparing likelihoods of models that have exactly the same number of parameters, you don't need to do the whole t-test thing, or you do the likelihood ratio test. You don't need to do that because they have the same number of parameters. And then it is simply enough then to gauge the relative quality of fit. So there's no surprise then in that scenario. The likelihood ratio test statistic, which you could calculate but not do any testing on, is the same as the AIC difference. Now these three different approaches have different theoretical properties. AIC is known in a prediction of mean square error sense, finds the best model which gives you the best predictions. BIC will find a true model if it exists, or a quasi-true model, which means it won't include spurious variables. That's a consistency property. And the likelihood ratio test is really a different thing. It's not trying to find a metric which measures the, which gives you a metric by which you can compare relative models. It simply says if you have one model, is adding extra parameters to that model, does that improve the likelihood by enough? So it's an asymmetric test in that sense. And whichever of these you should use, well, that's going to depend on what the purpose of your modelling is. This was explained in the journal Statistical Science in 2010, where Galich-Mweli had a paper called To Explain or To Predict. And to summarise what she was saying, she just said that AIC should be used for a prediction, BIC should be used if explanation is your goal, and testing should be done if you have a specific test, or if you have a specific effect or variable that you want to say whether it's important or not. I'm trying to say important rather than things like significant. Okay, so in practice, then, how useful is this distinction? There we go. Sorry, I was warned off using copyrighted material in this talk, so I normally have cartoons and things relevant to things like p-values, but I've had to just put some holiday snaps in instead. So the first section is AIC against p-values. AIC in practice. Well, from the famous Burnham and Anderson book, they say that, okay, AIC picks the best model, and if your model is within 2, then you have substantial support for that model as well as the best model. Considerably less if it's 4 to 7, and if the difference in AICs between two models is greater than 10, then the larger model is, or the model with the smaller AIC is, or so the larger AIC is basically there's no support for that model. I don't know what happens if you've got an AIC difference of 3 or 8 or 9, but anyway. And one of the claims that they make in this book is that the AIC approach is free from arbitrary significance levels. Arbitrary significance levels. However, in 2011, they published this set of delta AICs that were they thought were important, and it's different. That 14, by the way, which corresponds to equivocal, that corresponds to a likelihood ratio, I think, of over 1,000. That's actually quite different. Anyway. Okay, so last year in the journal Ecology, you may have seen this, there was a forum selection of articles on p-values and model selection. And I think the first of them was by Paul Murtaugh, called In Defense of P-Values. And to summarise that, he said, firstly, that delta AIC and the p-values you get from likelihood ratio tests are linked, as in the sense that there is a one-to-one mapping for any particular situation. He said that the criticisms of p-values which are there and they are valid, they're often more to do with misuse rather than the metric per se. He recommends saying, report p-values by all means, but always report effect sizes. I can't imagine any situation where you wouldn't want to do that, frankly. And he concludes that, look, all of these methods have their uses. And I've had to draw this. Okay, so this is one of his plots, and this is an illustration of the relationship between delta AIC and a p-value. And for different sample sizes, as I say, there is a one-to-one relationship. And if we look at some numbers in here, you'll favour a larger model if the delta AIC is positive. And looking up on here, the n is infinity line, that corresponds to a p-value of about 0.157. So that's interesting because that means that there's a model selection tool in this scenario where we've got two models which are differing by one parameter. If you had different numbers of parameters different, you'd get different curves. But for this situation, then the AIC is more liberal because it's going to include, if it's corresponding to a p-value of 0.157, it's going to be more willing to accept the larger model. You can go the other way. A p-value of 0.05 corresponds to an AIC roughly 2, which I think is one reason why AIC differences of 2 were often used in the past, ironically. Yes, I think I've said all that, haven't I? Yes, so the conclusion of that is that AIC, delta AIC and p-values are simply different points on the same curve because they're related. So they're not so different as some people might have you believe. This is an example that Adam Butler sent me. The variable names have been removed to protect the innocent. And this is a set of regressions that have been fitted. That's fine. You can see we have the coefficients and the standard errors. The coefficients are in bold if they're statistically significant. We have a column of AICs, delta AICs, and then the AIC weights computed from these delta AICs. The first thing to notice is that the model with variables 2 and 4 is the best by AIC. And the purpose of putting this up is to point out that, interestingly, the next 3 models in this table are all the best model plus one other variable. And if we think about it, going back to the definition of AIC, that's guaranteed to happen, almost. Because you're adding an extra parameter, the log likelihood is only going to go up, which means the deviance is only going to go down. And you are adding 2 for the penalty term. So your AIC differences, your delta AICs, cannot be more than 2 different from the best fitting model. And what that means is that even though you might have a variable that's, maybe this one is, that's completely unrelated to the response, it'll still be within 2 of the best AIC model. And as a consequence, in terms of the AIC weighting when you do model averaging, it'll have quite a high weight by definition. And that may or may not be a problem, but that's something that is worth worrying about. And this is what Burnham and Anderson say about that problem in the book. They say that any model that is within 2 of the best model, you should look at it, and if it differs by 1 parameter and has essentially the same values of the log likelihood as the best model, then the larger model is not really supported or competitive and is close only because it adds 1 parameter. And the fit is really not improved. Now, I never liked that particular section in Burnham and Anderson, and I couldn't really work out why until Monday this week, when I had a eureka moment. What they've just described there is exactly the rationale for doing a likelihood ratio test, because they're saying that the fit is improved a bit, but not enough by much. And how do you gauge whether a fit is improved by enough? Well, the standard way of doing that is a likelihood ratio test. Okay, so there is a bit of a muddle going on there with some of the arguments, I think. And this is another muddle of an argument, because they, again from the book, the Burnham and Anderson book, they hypothesize this situation where you've got, I think, 15 different models, all with the same AIC value. So they have one null model, or best model, and then models which are larger than that by this number of parameters, the J number of parameters. Now from that, given that we know they have the same AIC, you can work out the likelihood ratio test statistic, which is simply double the number of parameters in that case. And then you can do a likelihood ratio test and get the p-values. Now you'll notice that even though the AIC values are all the same for all these models, the p-values vary a lot. And Burnham and Anderson point to this and say that this is a dilemma, the solution to which is a matter of which model selection approach has a sound theoretical basis. AIC does, LRT does not. Well, that's nonsense. Because the whole point is you're asking 2 fundamentally different questions here. The AIC comparison is saying, is it worth me having all of these extra parameters in this larger model? Whereas the likelihood ratio test is saying, is it worth having any of those extra parameters? And that's a very, very different question, especially when you get down to 30. It is the same question when you've got a difference of 1, of course. But when you get down to 30, well, of course this is different. The AIC is quite ambivalent as to whether you should have the larger model, but the odds are that at least one of those parameters is worthwhile, which is why the p-value there is so tiny. So that's another example, I think, of muddled thinking in this stuff. The 0.157 is what we've seen already from Paul Murtaugh's plot. and we decided that this meant that AIC was rather liberal in terms of model selection. But what if, for example, you have a 10-level factor in your analysis? Well, if you have a 10-level factor, you'll be increasing the number of parameters by 9, which means that in that case, because the p-value is less than 0.05, but the AIC is flat, that means you're going to have AIC is effectively conservative, not liberal. So we thought that was interesting, at least. Yes, and this is the editorial. Okay, this heading, by the way, the uninformed pronunciamentos, that was also in the email by Stuart Hurlbert, and this is the editorial he was referring to, because the journal Basic and Applied Social Psychology have, well, they stated that they've banned p-values, but they've basically banned inference as far as we can tell, almost. well, seriously, I mean, if you're going to ban p-values, it does make sense to also ban confidence intervals because they are related. But they also, well, they're a bit sniffy about Bayesian ideas because they don't seem to know about the idea of informative priors, and they talk about, what does it say? Yes, they depend on some sort of Laplacian assumption to generate numbers where none exist. That's classic, not really understanding what you're talking about, isn't it? That's terrible. Anyway, so they kind of say that the way around this is simply to quote summary statistics and just get bigger data sets. Yeah. There we are. Oh, good. Very good. Okay, so that's AIC versus p-values. Now AIC and BIC. In the same series of articles, Ken Aho and colleagues had a discussion about AIC and BIC, and their summary was that in biology, the concept of a true model isn't particularly useful because it's going to be too complex to think about. The number of parameters that you would need are going to dwarf the size of your data set. So consistency, they claim, then is an irrelevant concept, which is true. There's no argument with that. But the question is, does that mean that BIC is not useful anymore? The paper which shows that AIC is optimal goes back to, well, certainly Shibata in Biometrika in 81, and they say that the regression function is specified by infinitely many non-zero parameters. That's the assumption they make, or by an increasing number of variables as n tends to infinity. So that's just saying that you'll never have all of the variables or enough data to be able to estimate the true model. And that's in terms of the sum of squared errors of predictions. But the assumption that is in there, remembering that this is an asymptotic result, is that future observations are from the same population as the current data. And unless you can absolutely guarantee that, then the optimality of AIC doesn't necessarily apply. In a sense, it's a form of stationarity assumption. It's not just that the means have to stay the same, or the effects have to stay the same. The distributions of covariates, etc., that you're sampling from have to stay the same. It's a strong form of stationarity, that's the word. Now, I don't want to fall into a trap. If I'm going to quickly summarize a simulation study, I'm not going to have the true model in the data set that I'm going to give the selection, and my aim is not going to be to select the true model. So if you do a sampling in this way, which Buckland et al. Point out, then of course you'll favour BIC because you've set the system up to favour it. Burnham and Anderson talk about tapering effects. I'll skip that one because it comes back later on. In terms of comparisons that have been done already, Paul Murtaugh had something in Ecology Letters where he did, again he was favouring, I think it was set up to favour BIC a little bit, and he said that there's no best method of selection. He even seemed to like stepwise a bit. There was a paper by Rafalovich which really did set things up to show that BIC was best, and they even liked stepwise regression. But goodness. Now this is a key claim from, again, another Burnham and Anderson paper. They say that criteria for computing model weights or model selection have optimal performance under different conditions. AIC for tapering effects, and BIC for either when there are no effects at all, or a few big effects and all the rest are zero. Okay, so if you've got a few strong effects, BIC should be best. If you've got sort of tapering effects going down to zero and possibly infinitely, then AIC is better. Okay, that's the claim. So let's examine that with a quick simulation study. Like I say, very simple, linear regression. I've got 10 variables in the generating model. For model 1, I'm going to have strong effects. Forgive this not being infinite. That's one of the criticisms, but okay, it's a small number. But I'm only going to give myself, in the data set, 5 of the variables in the generating model. And I'll add another 5 that are completely unrelated. everything's, this is not cherry picking. This is literally the first example we did. Everything's standard normal in terms of randomness. 1,000 simulations each for n going from 20 to 10,000. Model 2 is the same, except I'm going to have tapering effects. I've got 21 variables in the true model, and I'm again only going to give myself 5 of those. The effects, well, the x's are the real effects in the generating model. The coloured dots, or the filled in dots, that's the ones that are going to be supplied to me in the data set, and these ones are in the generating model, but they're not in the data set. And in terms of the tapering effects, well, I've got some sort of exponential thing going on. The dots here, the filled in dots, those are the variables, those are the effects for the variables which I'm going to have in my data set. So I've got a strong effect, a sort of medium effect, and then some small ones. And we'll see what happens. Well, what happens to a large extent, certainly when you're looking within sample, is pretty much what you'd expect. Certainly for smaller sample sizes, BIC has the problem that it misses a lot of the real effects for model 1, whereas for including spurious things, BIC does better because it's consistent. And notice that even as the sample size gets large, AIC has a tendency to include things which are actually spurious. But that's what we know. We know about all of that. For tapering effects, same for the Zs. And for the Xs, some of these effects are really, really small. So none of the methods are picking them all out, even for very large sample sizes. And to see where that comes, well, for the model with tapering effects, we can see that all of the methods get the big effect pretty well. They need a larger sample size for the medium size effect. They need really large sizes for the next one, or for the other two. There is no distinction in this data set. The analysis is unable to determine the difference between a really, really tiny real effect and a spurious effect. And that should surprise us, I think. Yes. So the root mean square error comparison, this is AIC's strong point. And we can see here that the red, that's AIC, that is always lower for the lower sample sizes. AIC is doing better in terms of mean square error prediction, as we would expect. And that's for both strong effects and tapering effects. But as I say, the problem is that future observations are from the same population as the current data is an important assumption. So let's try to not satisfy that. I say that not, I mean, out of sample, I'm going to consider two validation strategies. An out of sample one, where I simply get new X's and Z's, and then generate new Y's from the generating model for that, and see how well we can predict those values. And then what I call out of sample plus, where I actually resample means for the X's and Z's distributions. And I think that's justified in a kind of random effect sense, because often what we might do is fit a model on data from one site or location, and then try to predict values from another location. So in that sort of scenario, I think that's a valid thing to do. And if you do that, do a proper out-of-sample comparison, you discover that strangely enough, okay, I mean, here this does look like BIC is doing better in terms of mean square error, but actually I don't think there's much difference for the strong effects. But where there is a clear difference is in the tapering effects. Now remember, this is where AIC was meant to be doing really well, but actually it's the BIC that's doing better in that scenario. Now, yes, that was in the outer sample plus, because I actually thought I would need to go as far as that to get BIC looking optimal for the tapering effects, but actually even just simply resampling the X's and the Z's from exactly the same statistical distribution is enough to scupper the optimality of AIC in the tapering scenario. And that was quite surprising, how easy it was to do that. So why is there a difference? Well, the point is that BIC is simply just a stronger penalty. And it's less willing to include very, very tiny effects that might be real. But those very, very tiny effects which might be real will be estimated very poorly, relatively. And if you don't select that term, then you're effectively setting the effect to zero. And the truth is that many times a zero estimate is going to be better than the actual estimate from the data set. And even then, and also the fact that the X's and the Z's, even though they're sampled from the same distribution, they will have very slightly different properties. Now, all of that so far included, nearly there, all of that so far assumed that the X's and the Z's were independent. If you add correlations, then just to skip forward to the interesting stuff, the RMSEs, then yes, the AICs become, the performance is better again with mean square errors because they get extra, the fact that you've got everything's correlated means you've got extra help. And also, of course, remember in that case, if everything's correlated, if all your x's and your z's are correlated pairwise, then there is no such thing anymore as a spurious variable. So you can't distinguish between them. That's true, but that analysis assumed that the correlations were constant. But what if the correlations themselves vary? Well, effectively, I generated some random correlations between x's and the z's, bless you, and again, and perturbed them slightly, either slightly or quite a lot. And if you perturb the correlations slightly, you find that AIC works best. If you perturb them a lot, then BIC works best. And that again should be no surprise. The more unstable the situation is, the more you need to be conservative in terms of what variables you're selecting, which is why the stronger penalty of BIC seems to do better. And the theoretical properties that we've had and the hypothesized properties such as tapering effects don't seem to work. And the simplest way I think to look at this is just to say that AIC and BIC are different strengths of penalty. That's all they are. The properties of optimality don't necessarily work. So that's Bayes' tomb. Yes, some model misspecification. The key bit I think here, just have to hurry on, the problem is that there is a bias variance trade-off in any kind of model selection. If your model is too small, you'll suffer from omitted variable bias, but if your models are too large, then you get inflated variance problems. And the question is, under what scenario is a stronger penalty to give you a small model going to be better? Well, it's clearly going to be when the variability would otherwise outweigh the bias. It's that kind of trade-off. Yes, Hocking noticed this in '76 and gave some criterion for comparing the variability and the bias, but unfortunately that assumes that you know what the true model is, so it's not really useful, although it's interesting theoretically. And Liu and Liu, in the Journal of the Royal Statistical Society recently, suggested a generalized BIC, which is interesting. I mean, I know there have been lots of sort of generalized forms of these things and lots of different information criterion, but I thought this one was interesting because it allowed a decomposition of BIC into goodness of fit plus model complexity. Okay, that's BIC, the standard BIC, but also a separate term which is just model misspecification, which I thought was really interesting. The problem with that, though, is that, again, you need to know what the true model is, although they do suggest methods of bootstrapping. It was interesting to read a paper in a stats journal that said, hey, this method isn't ready yet, but they published it anyway, so that's good. I like that. Okay, I won't talk about terms. I won't talk about stability selection. So to summarize, model choice, you need to ask yourself what the purpose of the modeling is. That might give you a different approach. Whether your analysis is going to be exploratory or confirmatory, that might impact the size of penalty you're prepared to use. And for example, whether you want to develop a predictive model, which means you might need to do some experiments to work that out. Or you might want to particularly focus on testing a specific parameter or specific effect under a specific null hypothesis, in which case you'd be wanting to do some sort of test. Reproducibility has to be an issue in the scientific sense, because if you have a smaller penalty and you're more inclusive of variables, you might suffer more from reproducibility problems. Okay, I'll ignore the suggestions. That's the Frankfurt cider tram. And I just wanted to end up, okay, we're in the midst of a general election process going on at the moment in the UK. So I thought I'd talk about spin. Spin doesn't just occur in politics. This is a section from Burnham and Anderson's contribution to the p-value forum in Ecology last year. The section they have discussing p-values is called historical statistics. So what is the heading of the section that discusses AIC and so on? It's 21st century statistical science, which they then go and make a mockery of by talking about Kullback and Leibler 1951 and Bayes' theorem 1763. Nothing wrong with quoting either of those things, but yeah, just to say. And there we go, that's me. Thank you.
Okay, thanks for that. Am I on? Okay, thanks for that, Mark. And are there any questions whilst we have a quick turnaround with the computers in the next talk? Yeah. I'll just ask for one.
Thanks, Mark. Is the pragmatic solution just to do both?
No. I would have suggested on the slides there that you can test this, I think. Because if you have a data set, you could imagine creating a simulation study using the properties of the data set that you have for a given model or given set of models and seeing how well things predict. I guess the point is, it does go back again to what you want to do. What I've just said is probably valid if you're trying to predict. If you really do want to gauge the influence of a particular variable, that's not really the case for AIC because the penalty is too weak. And I think that shows that. And you're always going to be including things, you remember those plots, you're always going to be including things that are genuinely spurious. Does that answer your question?
Okay, just one more question.
How would leave one out cross-validation perform next to the? I mean, would it be similar to any one of those of AIC or BIC, or would it change depending on the model?
It would be closer to AIC because AIC is they are equivalent asymptotically, AIC and leave one out cross-validation. There is an issue with cross-validation, and that's that if you have one data set and you split it up into bits and then you do a cross-validation, you haven't really done, to my mind, an out-of-sample validation because it's still the one sample. A slide I skipped through there was to do with analysis we did with terns, where we had terns data on lots of different colonies, and we did a cross-validation by colony because we thought it was reasonable to treat those as different data sets. And what we found doing that was that if we did that way, that cross-validation by colony, we ended up picking very much smaller models because you were overfitting to specific colonies otherwise, if that makes sense.